So, hello everyone, hope you are doing good. Welcome to the day 23rd of the Daily Leetcode Challenge. Today we have a medium level question with us, and it's a very tricky one. Let me tell you at the starting itself, it's really tricky one. I have tried many approaches to solve this question, but it is accepted only a particular approach solutions, right? It's a disadvantage, but let us see how to solve that approach. The idea is they are trying to teach one particular concept as a way to solve this question, and they are accepting only such solutions, right? So, let me tell you what the question is. So see the it's question 1319 and the name is number of operations to make network connected. So what is given to us is we are given the number of nodes in this connection, right? For example, in this diagram you can see 0, 1, 2, and 3. Okay, the number computers are numbered from 0 to n minus 1, and this n value is given to us as an input, right? Then you are given a connections array. What connections array is? Connections array is it's showing how the computers are connected, the connection of Ethernet cables, forming a network where connection of I is equal to A of I, B of I, representing a connection between computer A and I and B and I. What that means is 0 and 1 is given, right? That means 0 and 1 are connected through Ethernet cable. Means 0 and 1 are computers basically, and this is the number of computers, right? Similarly, 0 and 2 means there is a connection between 0 and 2 computers, right? Computer number are marked with 0 and computer number marked with 2. And similarly, 1 comma 2 means there is a connection between computer 1 and computer 2, right? So that is the what is meant by the connection array, and then is the number of computers. So what is the ask of the question, right? That we have to see. You are given initial computer network connections. You can extract certain number of cables between two directly connected computers and place them between any pair of disconnected computers. See, this is the keyword involved here. The whole question revolves around this disconnected computers to make them directly connected. Return minimum number of times. Okay, return the minimum number of times you need to do this in order to make all the computers connected. If it is not possible, return -1. See, there are only two concepts here. Okay, which will decide the answer. The first part is if there are n connect. See, if there are n nodes, we need a minimum of n-1 edges, right? This is a simple math logic. See this question. If you want to know what are the topics involved in this question, it's very simple. It's DFS. You can also solve this question using union find. It's BFS, and then there's simple maths involved as well. Okay, hashing and maths. So these are the topics if you want to know how to solve these questions. But they are only following one idea here to solve this question. What is that? See 2 points in that. First point is if there are n nodes, right? There has to be a minimum of n-1 edges. Otherwise, we cannot connect them. I'm talking about nodes, right? If there are n nodes, there has to be a minimum of n-1 edges. Next comes the idea of connected components. If we have C connected components, we require at least C-1 edges to connect them. If there are more than C-1 edges, it is well and good, right? But at least C-1 edges are required to connect them. So what is the difference between statement 1 and statement 2, which I mentioned just now? The first statement tells about nodes, second statement tells about connected components. What is the first statement? There has to be n-1 edges for n nodes. Second statement tells that there has to be C-1 edges for C connected components. That is what we are going to do. Okay. So this is the first statement. Based on the first statement, we are writing this code. For n edges, there has to be at least n-1. See, for n nodes, we need at least n-1 edges. If the number of edges is below that, we cannot solve this question. We have written -1, right? Next part is see the next logic comes in terms of connected components. Okay, so this part of code comes from the statement 1, and the rest of the code is fully based on statement 2, which tells that for C connected components we need C-1 edges. What it means is that see, if I have a connected component, see what I will do is I will find the number of connected components. In this diagram you can clearly see first I have ensured that I have enough number of edges. Point number one is clear, right? I have enough number of edges to connect all the computers. Next is if I will try to find how many disconnected components I have. In this diagram you can clearly see 0, 1 and 2 are a single connected component, and 3 is a disconnected component. We can say C is also a connected component in itself. So total number of connected components which are not internally connected are 2, right? So for connecting two connected components, how many edges we need? 2 minus 1, which is 1. So the answer is 1 here, right? Now come to example 2. Please rewind and see this part if you have any doubt. Okay. So here you can see there is one connector component marked in blue, right? One connector component marked in blue. 4 and 5 are two different connector components. So total how many connector components we have? One, two, and three, right? There are three connector components. This full blue one, this four, and this five. Now let us see. First let us check if we have enough number of edges or not. N minus one is 5. Do we have at least 5 edges? One, two, three, four, five. Yeah, we have at least 5 edges. That means connections are possible. This is in terms of nodes, right? We have not seen in terms of connector components till now. We have three connected components, and we already know that there is see number of edges are enough, right? 6 minus 5, 6 minus 1 is 5, which is there. Okay, so now there are three connected components, so we need 3 minus 1 is equal to 2. Okay, that is the answer here. Coming to example 6, 6 minus 1 is 5. There has to at least 5 edges. Do we have that? Here only 4 edges are present. That means it's not possible. There are not enough cables. So from the example, at least you would have understood that this question can be solved by dividing it into two parts. First part, we check if there are enough number of edges, irrespective of the number of components. If there are enough edges, for that what we are doing, we have to ensure that there are at least n minus 1 edges for n nodes. Next, coming to connected components. If we have the first condition satisfied, that is enough number of edges are present, then we are trying to check if we are trying to find basically the number of connected components. And if we have the number of connected components, the answer will be C minus 1. Okay. See, this is possible only because of the first statement, right? There are first we ensure there are enough number of edges. Only if there are enough number of edges, we can say that the number of the answer in this case will be C minus 1, because C is the number of connected components, and for C components we require at least C minus 1 wires to connect them extra. Okay, so this part is based on the first statement, and here we are trying to find the number of connected components. So this whole part. Okay, what I'm doing is I am taking an edge array, I'm initializing it. Okay, I will just print and show you how it works. Okay, yeah, let me print and show you. So this is how it will look. In the okay, after that also I will have to print here. We'll just first show you how it looks. See, this is how my array will be in the starting. Sorry, the map will be, the hashing will be in the starting. And here for each node 0, I will be like keeping in a list the number of connected nodes. Okay, 0 is connected to node 1 and node 2. Similarly, node 1 is connected to node 0 and node 2. Similarly, node 2 is connected to node 0 and node 1, right? And this is a visited array. Visited array is a true false. See, for each node, we will have a false or true component. If it is false, means it is not visited in our BFS traversal. This thing we are using to track which nodes are unvisited. So, see, the idea is to find number of connected components, right? That is what we are doing here, right? So, yeah. So this part is clear. See here, it's very simple. We are going to connections array. This is a connection array. Clearly, it is showing a connection between 0 and 1. So for 0, 1 is the node which is connected, and similarly for 1, 0 is the node which is connected. So for A, I am appending B. For B, I am appending A, right? Remember, H is a mapping, right? Hash map. That it has a key value pair, right? Similarly, visited is a list this time. For each node I, see it is of length n, right? So for each node I, there is a true or false value. It can be only one value, either true or false, right? Now number of connected components equal to 0. I'm initializing it with 0. See, the final answer is going to be number of connected components minus 1. Okay. So I am going through each of the nodes, right? For each node I am checking if it is visited or not. If it is not visited, only then I am marking it true and I'm starting BFS from it. So please make these points very clear if you note anywhere. For I am going through each node first, I will check if it is connected or not. That means if we have visited it or not. If we have not visited it, start BFS. Before starting the BFS, we are initializing some values. First of all, we are making it visited as true. See, in this case, what see there are different ways of doing it. In this case, before we are entering the node into the queue, we are making it listed as true. Okay, please note these points. Then we are increasing the number of connector components by one, and then we are starting the BFS. BFS, if you know already, then you must be by now thorough that we will be using a queue, right? Queue is a queue here which has a value I. Run this value till my queue is not empty. Okay, I will pop the leftmost element of the queue and store it in the node car. Car is like 0, 1, 2, like that value should be there. Car means 0 node or first node, second node, like that. For child in edge of car, okay, what I'm doing here is I'm iterating through the nodes which are connected to this current variable. Okay, current means current variable, current node. Okay, so child is the adjacent node of the current node. If visit of child is false, that means if child is not visited, make it as true and then insert it in the queue. Already told you that in this case, before inserting a node, I am making it visited as true. This is the logic I'm following, right? This is what we're doing. See, what will happen is if you see this example, first 0, 1, and 2 will be inserted, right? And the loop and the time will come when this while loop will stop because the queue will get empty. Now, because of this for loop, we will be able to reach 3, right? We will be able to reach 3 again. And again, these things will follow. The number of connected components will increase. It will become 2 now. And again, a simple queue will be initialized with 3 and a simple VFS will happen. And because it's a single node, nothing will happen much. So number of components will become 2, right? And finally, we'll be returning 2 minus 1 is the answer for the first example. So friends, I will again repeat this question. There are two parts. First part is we are checking for the given number of nodes if there are enough edges or not. And then we are checking if for the given number of components, we are trying to find what is the given number of connected components and we are returning the answer as number of connected components minus 1. See, the second part cannot be done without the first part, right? There has to be enough number of edges for the end nodes first. If only in that case, we can go for finding the number of connected components, returning minus 1 is the answer, right? If you talk about this solution, let me show you that this solution, yeah, it beats 91% of the cases, right? So, coming to the time and space complexity of it, see, it's a BFS traversal, so O of n plus C is the time complexity, n is the number of nodes, E is the number of edges, right? Coming to space complexity, see, we are having an array, which for the visited array, it's O of 1. At the same time, we are storing, see, the edges as well, the number of edges and nodes and edges. It's basically the number of edges, right? So in total, if you see, even the space complexity is like O of n plus E, where n is the number of nodes and E is the number of edges. Okay. So if you have any doubts, please comment below. See, the purpose of making videos on this topic is to discuss further. See, it's a tricky question. I understand that it's a tricky question. I have myself tried many ways to solve it, but they were not getting accepted. In the last final two cases, case 35 and case 34 of the test cases, is getting failed. I understand that, but please share your approaches. We can try further and try to dig out why it's happening like that. Okay. If you have any doubts in the current approach, please approach me in the comments, and I will definitely answer them. That is all for today, friends. Please support my efforts. If you really like the video, please like, share, and subscribe. Thank you. Thanks for today.